Okay, everybody, we've been going over heat strips in the last 7 videos. I'm going to go ahead and just tie the knot on heat strips and introduce defrost control boards. How I'm going to do that is I'm going to go over a very similar problem throughout our industry that you guys can probably agree to. It's called cold blow, and cold blow is not well understood because heat strips aren't well understood and defrost control boards aren't well understood. So I'm going to try to simplify both the primary function of the defrost control board and the primary function of these heat strips on a 2-stage system. I have a pressure temperature chart. I've got a diagram of the refrigerant circuit. You can see there's a liquid line. I've identified things as much as possible. I'm going to try to quickly go over it. You can always pause the video and read this stuff here. Just to quickly go over it. We have our liquid line here, the bidirectional dryer, biflow dryer. We have an expansion valve on each end. We have an evaporator coil. We have our gas lines and our capillary tubes. We have our condenser coil with gas lines and capillary tubes. We have our condenser fan motor. The arrows obviously indicate that the air is moving through the coil and up. We have the blower motor here, section of heat strips up here. We have the arrows going up indicating air moving across the coil. You'll notice that I have lines with PSI and lines with temperatures where we're going to be seeing what temperatures are throughout the entire diagram. Accumulator, compressor, reversing valve, defrost control board. Over here, picture of my thumb, the rule of thumb. And then, of course, we have identified where high pressure and low pressure are going to be at all times, whether it's in heat or cool. And what state the refrigerant should be in, whether it's vapor hot or vapor cool, or high pressure and then liquid. So if you notice, the condenser coil is blank and the evaporator coil is blank. We're not using red or blue starting off. So what you need to think of, whether this is in heat or cool, or whether this is in heat or cool, at no matter what. Okay, it doesn't matter where my reversing valve is resting, whether it's in the heat mode or the cool mode, it does not matter. I will always be at these values. Okay, these values of liquid, the values of vapor. And so always refrain back to this because I'm always in this state no matter what, heat or cool. The critical component, as I call it, the critical component, the first one, the compressor, this is where we're going to get our temperature rise. Okay, we're not changing any states. We should be vapor in, vapor out. And then our second critical component, there's 2 of them, right? If we're in heat mode, we're using the one for the outside. If we're in cool mode, we're using the one for the inside. In this situation, we're talking about cold blow, so we're referring to what happens during defrost, so obviously what happens during the heating cycle. So we're going to say our critical component, or second one, would be the outside expansion valve. So I'm going to go ahead and list pressures on both sides of the valves, pressures on both sides of the compressor, pressures, entering coils and leaving coils, and what these temperatures could be based on a cold night. We're going to talk a little bit about the defrost control board, a little bit about the heat strips, but I believe this entire process should put a lot of light on what we call cold blow. Cold blow is best going to be described once I draw colors on this diagram, right? So we can read about it or talk about it. I think once we put some color to this, I think it's going to be well expressed. I have a pressure temperature chart over here for 410A. And I'm going to go ahead and just put 2 values that we need to start off with. One, a room temperature, and 2, an outside temperature. We're calling it the ambient temperature. So we're going to go ahead and put those 2 values down. And based off of that, we should be able to get a pressure. That pressure will allow us to fill in the rest of these blanks. All right, so the given scenario is the outside temperature, which I'm going to do in blue because obviously we use blue for low, red for high. We're going to say it's 42 degrees outside. 42 degrees Fahrenheit. Now if we look here, the rule of thumb, okay, when we're dealing with pressure, the rule of thumb is 20 to 25 degrees colder than the ambient temperature during heat mode. And we're referring to the condenser coil. Okay, so if I had to say, well, am I overcharged or undercharged? You know, am I restricted? Am I not restricted? Just a good rule of thumb would be, if I'm 42 degrees outside, let's go ahead and subtract 20, see where that lands on the pressure temperature chart. So go ahead and we'll do a couple of values here. And we'll say 42 minus 20 gives us 22. All right, so 22 would be 81.8. I'm going to go ahead and round up and say 82 psi. All right, so I'm going to say 82 psi would be the value for 42. I'm just going to make a note over here. 82 psi, and we'll come back to that. We're going to say the next value, the room temperature is 72 degrees. And notice I used red because that's warmer than blue. And so 72 degrees is warmer than 42 degrees. So we're going to use the color red for that. So 72 will be the room temperature. I'm going to roughly add about 20 degrees on top of that and say we're 92. Will put us right around here. We're going to say 274. So we're going to put in parentheses here 274 psi, and that will be everything that we, and remember, this is just a scenario, so this doesn't guarantee that, you know, 20 degrees or 25 degrees is gonna be that every time. There's a lot of things that could change that. Dirty coils, not properly charged systems, poor airflow, maybe based off of RPM not being matched up just right. Maybe somebody put a motor in there, those fan blades aren't sitting in that shroud, so we're not moving air effectively across the coil. There's a lot of variables, dirty filters, dirty coils here, poor airflow. There's a lot that can go into this. So don't sit here and look at that and go, well, Tom said it's got to be 274 psi if I'm 72 degrees inside. That's just what has to happen, because that's not what I'm saying at all. We're just trying to come up with something that we can work with here. And this is just a general rule of thumb based on everything pretty much being what it's supposed to be. So if I have the system that is in heat mode, then what's going to happen, my hot gas is going to come out, it's going to come down, and it's going to flow through my discharge line, through my reversing valve. It's going to come around and it's going to enter into my condenser coil. Okay? It's going to fill up. It's going to condense, and we're going to come back through the TXV in a liquid state. And that would be actually cool mode. That will not be heat mode. So to finish this off in cool mode, we're going to return back in a low pressure, we're going to go through the reversing valve, we're going to come up through the accumulator and into the compressor, and we're going to pick up heat of compression, which will give us back our high pressure. So I'm going to do that again and put color to these evaporator coils and then break that down a little bit better. Let's see if I can undo this without erasing a lot of it. There we go. That worked out. Okay. All right, so right now, we don't know what mode we're in. We just know we're 42 degrees, 72 degrees. We're going to go ahead and say that the outdoor unit is in heat mode. So it's going to be, the whole thing's going to be under low pressure. We're going to say the air handler is now going to be red because we have hot gas flowing into it. We're going to move our valve over. The valve's in the heat mode position, and hot gas leaves the compressor, flows through the reversing valve and into the evaporator. And so we're going to write some values down, and that should help better express what we're looking for here. All right, so if I'm running 82 psi, then I'm going to have that value here. As a matter of fact, I'm going to go ahead and put that in blue. That'll help us out. So we're going to say 82 psi. Our true suction is always suction is 82 psi. Over here, we're going to be 82 psi. On this side of the expansion valve, we're going to be 82 psi. So here's all my values based on 42 degrees. Rule of thumb, I'll be 82 psi everywhere that follows. As far as the discharge, we said 72 room temp, 274 psi. So we'll say 274 going into the reversing valve. Coming over to the evaporator coil, 274. Okay, leaving my evaporator coil condensed at the same pressure, 274. Bypassing the expansion valve, we're not metering, so we're liquid, but we're the same pressure, 274. Right before we meter, the pressure drop over here at this expansion valve, we are 274, and on the other side of it, immediately we're 82. And so we're 274, 82, 82, all the way through the reversing valve, 82 psi, across the accumulator, into the compressor. We pick up heat of compression. We're still in a vapor state. We have now increased, and we're at 274 psi. And as the room temperature changes, down or up, the head pressure is going to follow down or up based on that temperature. As the outdoor temperature drops or goes up, the outside PSI for the low side, it's going to go up or down based on that temperature as well. This is just a good rule of thumb. And so if we wanted to look at what this would look like in color form, let me go ahead and get that mark bigger. As that discharge gas comes across this reversing valve, it can only go in one direction because the valve is shifted over to the far left, blocking it from going to the condenser coil. So it's entering, this hot gas is entering this evaporator coil, and as that air moves across that coil, we're taking that warm air and we're dispersing it throughout the entire house. And as that 72 degrees, which is obviously much cooler than the hot gas, it's allowing that gas to condense down to a liquid. Once we go through the liquid line, going through the biflow, we sit and we have a pressure drop, which drops that back down to a low PSI. And then at this point, we change our color We come through, we go through the reversing valve. We're at a low pressure vapor. We come through, go through our accumulator. Any oil will get picked up from the accumulator that was deposited there throughout the other run cycles, and that will lubricate our compressor inner working part, so we're not having too much friction. Now, this is pretty much everything you already know if you've done heat pumps. The entire flow is reversed for cool mode, like I started off in the video. What happens is this defrost control board has two features on it. One feature is a time defrost. The second feature is a forced defrost. So if this is running, say if there's a 30, 60, 90, once it hits 30 minutes of runtime, 60 minutes of runtime, or 90 minutes of runtime, this will go into a timed defrost. If it needs to go through a defrost cycle before then, it'll go through a forced defrost cycle based on the defrost temperature sensor closing, allowing 24 volts back on the DFT part of the board because the sensor closed on temperature fall because too much ice formed around that sensor. And we're going to have tons of videos on defrost control boards where we'll cover all that in detail. But for this, three things need to happen. The three things that need to happen so you can diagnose things properly, especially cold blow, is one, the condenser fan's supposed to shut off. So these arrows theoretically are no longer here at this point the moment that fan shuts off. The reversing valve is going to shift over, excuse me. Matter of fact, we'll just go ahead and get rid of these. As many of these as possible. There we go. The reversing valve is going to shift over to the far right, and this discharge is going to now come into the condenser coil. As that happens, we are now changing states, and now we have hot gas entering the evaporator coil, condensing liquid on our liquid line, and now we're boiling off on our evaporator coil, and that is actually, excuse me, that is under a low pressure. So you got to think about this for a quick second. Fan motor shut off, reversing valve switches over. We're in AC mode. That is exactly what AC mode looks like. Let's look at this for a second. Hot gas comes over, is now coming into the condenser coil. Liquid is leaving the condenser coil. All right. We now have a pressure drop on this expansion valve. Okay. Then we'll go ahead and look and see what that looks like. I'm going to change these values up here. The 274 is going to be the same. Lots of values here. Okay. All right. And so we said we would use colors on these values. And so over here I have 274, excuse me. I have 274 PSI. If I have 274 there, I've got 274 leaving. There is no pressure drop now, so I have 274 again on the other side of my expansion valve. That means I have 274 here, and then my pressure drop would be roughly right around in this area here, which if I have 72 going across it, minus 20, that's going to be what, right around 52. It's going to put me right around 142. And so 142 PSI leaving the evaporator coil, I'm going to be 142 psi. We're going to go ahead and continue our journey. We're going to leave our evaporator coil. We're going to go through our reversing valve. We're going to come back up into the accumulator, out of the accumulator, back to the compressor. And those values will be 142 again here and 142 again here. So we're going to put 142, oops, excuse me. $142, $142. All right, so 142, 142. So there's pretty much all of our pressures. Now let's look what's going on here. We're in this mode. We are in defrost mode at this point. What is my temperature once I come across this evaporator coil? All right, in cool mode, I'm going to be roughly around 52 degrees, right? So 52 degrees, it's pretty cold. I'm going to go inside my blower, all right, at 52 degrees. I'm going to come out the top of my blower at 52 degrees. And if these heat strips never came on because the W2 was never energizing my strips, either because the wire was not connected right, not wired right, W2 wasn't energized because the board was bad, heat strips aren't working properly, any scenario you could possibly think of. If these heat strips do not come on, then now I have 52 degrees coming out of the top into my plenum. And what happens is throughout the night, you're dropping the temperature multiple times when you go through a defrost cycle. And so when you come out of a defrost cycle, yeah, you're warming it back up, but it's going to run longer now because it's got to catch up on what it lost. So if you're maintaining 72 degrees inside a house, and this happens around 1 a.m., then by the time it's 7 in the morning, the house could be down to, 45, 50 degrees. And, by the time you get out there around 1 o'clock in the afternoon to look at it, the house may be back up to room temperature of 72, where the set point was at that point in time. Technician may not understand cold blow and may say everything's working fine because it's not a refrigerant problem. It's the fact that during defrost cycle, you were in air conditioning mode and the heat strips never came on. Now, if you wanted to look at what would happen if the heat strips did come on. The heat strips did come on. All right. We activated these heat strips. Then these heating elements, whether it's 5K, 8K, 10K, all right, 52 degrees off the coil, 52 degrees through my blower, across my heat strips. The heat strips are now going to warm that back up, and we should be looking at somewhere around, I would say, 75 degrees maybe. Now 75 degrees may feel cold, it may feel cool because it's not 100 degrees or 120 degrees like your heat pump normally produces with heat strips, but at the end of the day, 75 degrees isn't 52 degrees, and 75 degrees is not going to drop the room temperature. What it will do is it'll maintain. So it's not going to really warm up, it's not going to cool down. During that 1 minute defrost cycle, multiple times throughout the early morning hours or late evening hours, it's just not going to shut off fast or drop the temperature. It's just going to maintain that. So you take that out of the equation and you have what's called cold blow. That's as simply as it can be put. In understanding cold blow, it's pretty difficult to not know heat strips, and pretty difficult to understand it without knowing your heat pump, the process of where the hot gas is going, okay, and what three things my defrost control board are doing. As we start getting into defrost controls, we're going to hit on many things, what the heat pump's supposed to be doing, the heat strips, what they're supposed to be doing, but we have to assume that there's already a video out there that you're watching, that you're following along with. So as we talk about those things, we don't have to spend too much time going over how they work. And so we'll start our introduction into defrost control boards on our next videos. Please continue to follow us. Thank you.